Okay, okay guys. Sorry for the wait. So let's get back into it. Here's our plan. You define N to be the smallest inductive set. You need an axiom for this. We kind of get principle of mathematical induction for free. Well, that comes from the axiom. We define less than. And then we need to define plus times. So like, then using those, we want all the nice properties of the natural numbers. Like, just as an example, we want to show that, you know, if m is less than n, then m plus k is less than n plus k, for example. And of course, multiplication, addition, and less than, they all work together in these different ways, right? Okay, so that is our plan. Okay. So our next step is to define the natural numbers. Well, we want it to be the smallest inductive set. So this is just like the kind of usual trick. I want something to be the smallest set having some property. I kind of define it to be the intersection of all the sets having that property. So for the natural numbers, that means define it like natural numbers, a set of natural numbers denoted with like a bold N is, it's just like the set of all n's such that n is an element of I for every inductive set I. Okay. And there is a problem. There's a problem if there's no inductive sets. If there are no inductive sets, then this definition is the same as the definition of n, such that, you know, n equals n or something, like n. You know, in other words, this is like the set of everything or the universe, which we know would give us a contradiction. We don't want to concept. This is called the Axiom of Infinity. And it says an inductive set exists. Oops, I wrote an inductive exists, but I meant an inductive set exists. Okay. Now our definition of the natural numbers is well defined. We want the Okay. And now you can see we kind of, from the axiom of it is an infinite set, because if n is a natural number, then n plus 1 is a natural number. We can always add 1 and find a bigger natural number. Okay. So one of the axioms which was desirable was that the natural numbers are unbounded, and defining the, okay, but we'll get to that later. For now, the natural numbers is a set. That's good. We're in set theory, so kind of we're stuck if it's not a set. Not only that, it's an inductive set. And of course, for all inductive sets, I okay. So proof, let's just, we're not always going to be so careful, but, let's be careful for a little bit. Let's show that n is a set and n is an, well, the axiom of infinity lets us say that let I be an inductive set by axiom scheme of comprehension. We can look at the elements of I that are in every inductive set, such that X's and J are all. This is a set. Okay. And then this is just the natural numbers. Okay, so we have a set. We have the set of natural numbers. And now we want to show that the set of natural numbers is inductive. Okay. First of all, I'll have 0 as an element. Okay, so 0 satisfies the sentence, so 0 is a natural number. Now, suppose n is a natural number. Well, since the natural numbers are the set of all elements in every inductive set, n is in I. Since n is in I and I is inductive, n plus 1 is also in I. Therefore, n plus 1 is in the inductive set I. Since n is in I and I is inductive. Okay. And then we've shown, so I was just an arbitrary inductive set. So n plus 1 is in all the inductive sets. Because this n plus set of all things which are in all the inductive sets. Okay. And that shows that 0 is a natural number. And if n is a natural number, then n plus 1 is a. Okay, and that's the proof of 2. So n is an inductive set. Okay. So basically, as a result of this definition, we get the principle of mathematical induction. So according to the notes, I should talk about less than symbol first. Okay. First of all, we should 0, 1, 2, 3, 4 are all natural numbers. 0 is a natural number. Well, since 0 is a natural number and the natural numbers are inductive, 1, which is 0 plus 1, is also a natural number. 2, which is just 1 plus 1, is also a natural number. 3, which is just 2 plus 1, is also a natural number. You know, and you can go as far as you can write, but yeah. So far we have you know, the natural numbers start from 0 and as high as you can count, you can. Also, there's also a kind of a natural way to define less than. Basically, if a number comes before, if you count starting from 0, you know, if you reach 2 before you reach, okay. So there's like, just by counting, there's a natural way to order the natural numbers. And it turns out that we can capture that by this following definition. So let n and m be natural numbers, and define less than by if n is an element of n. Now, we can show, like, let x be a set then x is always going to be less than x plus 1. Why? Well, the definition of x plus 1 just says take x and take the union of, and so x is in a singleton containing x, and that's a subset of x plus 1. So x is in x plus 1. X is always an element of x plus 1. In other words, x is less than x plus 1. Okay. So now we have a nice ordering. Okay, which is pretty good. So, you know, that means like you can, you know, any like 5-year-olds, you can reassure that the way they are counting is, you know, mathematically consistent, which I'm sure they were very worried about. Okay. But we want more than that, you know, we want the obvious things to be true. Like we know that 2 is going to be less than 3. Why? Well, because 3, which is just 2 union the singleton of 2, which is 0, 1, 2. So is an element of that. So that means 2 is less than 3. And we know that 3 is less than 4. Well, because containing 3, which has 3 as an element. If you want, this is just 0, 1, 2, 3. Okay. And then we want to make sure that 2 should be like less than 4, for example, because we want less than to be a strict ordering, meaning a transitive relation on the natural numbers. Now here's where all the terminology comes in. And such that is asymmetric, which means that, you know, if 2 is less than 3, we don't want 3 to also be less than 2. Okay. This is the number 4, and 2 is right there, because 4 is just the set 0, 1, 2, 3. And you'll notice like 4 really does contain all the numbers that are less than it. So this is where this definition of less than comes from. Okay. So the next, what we should, like, kind of our next goal is that, you know, we want to show that less than, where's the goal for possibly today? Prove less than is transitive. Asymmetric. And also, we will also want to add for all natural numbers n and m, exactly 1, either n is less than m is less than n, or n equals m. One of those holds. Okay. And this turns out to be pretty involved. So luckily we get the principle of mathematical induction for everything you get for free. Everything else we have to work hard for. Okay. So we have theorem, principle of mathematical induction, and then we have to use induction to prove these properties of less than. And then, you know, even after we do that, we haven't even defined addition, but that's how it goes, I guess. Yes. What's the theorem? What's the principle of mathematical induction? Probably you might know. So let P of X assume P of 0, and assume that for all n, if P of n, then P of n plus 1. Then under those assumptions, for all integers n, or sorry, for all natural numbers n, P of n holds. Okay. Proof. Well, we just let I, this is going to be the set of all natural numbers n, such that P of n holds. Well, then I is definitely a subset of the natural numbers. We want to show I equals the natural numbers. If I equals the natural numbers, then P of n holds for all natural numbers n. Okay. But 0 is in I. That's because P of 0 holds. Also, if n is in I, then n is a natural number, and P of n plus 1 holds. This is like the B assumption, part B. I guess I'll call it assumption So if n is in I, then so we've shown that I contains 0, and if n is in I, then n plus 1 is in I, so I is an inductive set. In it, because the natural numbers are contained in every inductive set. And therefore we can say, well, I is contained in the natural numbers, which is, and that tells us that P of n holds for all n as required. So that tells us the principle of mathematical induction is really embedded into the definition of the natural numbers. Okay. Okay, now we have to somehow, we have to prove, basically we have to prove like transitivity of less than and all that stuff. The only tool we have is induction. Okay. But we can start slowly. So let's first prove this proposition. For all natural numbers n, 0 is less than or equal to n. And for all natural numbers k and n, we have that k is less than n plus 1, if and only if n. Okay. And let me just tell you, less than or equal to is exactly what it says. Let's just do an aside. Note, m less than or equal to. It's m is less than n or m equals n, just like you think it should be. Or I hope you think that. Okay. So we'll just start simply two kind of obvious things. We want 0 to be, k to be strictly less than n plus 1 if and only if k is less than or equal to n. Okay, proof. So we'll first define P of n to be the statement that 0 is less than or equal to n. And we'll prove P of n by induction. So P of 0, that's the statement which is true since 0 equals 0. Okay, so P of 0 holds. Now assume P of n, in other words, assume 0 is less than or equal to n. The definition of less than or equal to says okay, and we have to show that 0 is less than or equal to n plus 1. So we want to show, well, if n equals 0, now n plus 1 is equal to 0 plus 1 is just 1, which is the singleton 0. 0 is in 1. So 0 is less than 1. And that means, well, n was 0, so 0 is less than n plus 1. Okay, check. The other possibility was that 0 is less than n. Well, the definition of less than means that 0 is an element of n. And n is a subset of n union, the singleton of n, which is just another word for n plus 1. So now 0 is in n is a subset of n plus 1. In other words, 0 is less than n plus 1. Okay, so in either case, 0 is less than n plus 1. So p of n plus 1, that completes. So now by principle of mathematical induction, 0 is less than or equal to n for all n. Okay. And now we have this, you know, we have proved one of these most basic things that everyone knows that, okay, let's do the other side over here, why not? Okay, so suppose k is less than n plus 1. We need to show that k is less than n or k equals n. Well, n plus 1, so k is less than n plus 1 implies that k is in n union n. Now the definition of union means that k is either in n or this singleton. So either k is in n, well, if k is in n, and what we wanted to show was that either k is less than n or k equals n, and that's we've shown that. Okay, and the other case is that k is in the singleton